Good day, everybody. Today, we'll be talking about chemical reactions. In this chapter, first, we'll introduce to you the evidences of a chemical reaction. Then, we'll talk about how to balance a chemical reaction. We'll continue and focus on what are electrolytes and non-electrolytes. Following that, we'll be talking about solubility rules. We'll also talk about different ways to write a chemical reaction. In the end, we'll be talking about the different types of chemical reaction. Here are some of the evidences for a chemical reaction. For example, you might see a color change. You might see the formation of a solid from a previously clear solution. You might see the formation of a gas when you add a reagent to the solution. You might see the emission of light or emission or absorption of heat. However, do remember, all these evidences cannot single-handedly conclude the reaction has already happened. We can be fooled. The only way that we can tell if a reaction has happened or not is by chemical analysis, which we will talk about. So let's give you one example that shows you why those evidences we just listed might fool us. For example, the formation of gas will happen when you boil water, because water converts from liquid water to the gas phase, which is water vapor. However, before and after this process, it stays as H2O. The identity of the molecule has not changed. So, as you can see, although in this case we do see the formation of a gas, but this process is not a chemical reaction. Rather, this process is a physical change. Let's look at another example. For example, in iodine sublimation, we do see iodine in the solid phase, S represents solid, is being changed to iodine gas phase. Okay, this is so-called a sublimation. When we look at the color change in this process, iodine in the solid phase is like a dark color or black color. However, in the gas phase, it's more like a purple color. Okay, we do see the color change. However, this is not a good indication of a chemical change, because color can change in different phases for the same substance. As a matter of fact, this process is a physical change, because before and after the transformation, iodine stayed as I2. The identity of the substance has not changed. So this is a physical change. So it's really important to know color can be different even for the same compound in different physical states. For example, if you have a red color, it's dissolved in water, and you keep diluting it, red will become pink and eventually light pink and disappear. But if the color before and after the transformation is totally different, this might be a good indication of a chemical reaction. However, for any conclusive evidence, you should look for the chemical analysis to determine the identity or the composition before and after the transformation. If the composition or structure of the substance has changed, then this is a chemical reaction. Or else, if the identity has not changed before and after, then it is a physical change. Let's look at a few examples. Which of the following is the evidence that a chemical reaction has occurred? So when we look at that, formation of a precipitate or a solid. That's the same chemical term. Color change, emission of light, evolution of gas. All of this are evidences for a chemical reaction. However, do remember, only chemical analysis can determine if a reaction has happened or not. Next question. Which of the following is not an example of a chemical reaction? Digesting a candy bar. Digesting a candy bar, we change the candy bar to something else using the digestive system. The candy bar has changed to something else. So this is a chemical change. Burning propane in the gas stove. Burning or combustion is the reaction between the fuel, propane, with oxygen, which generates different substances, carbon dioxide and water as the products. Grinding coffee beans, you did not change the substances or the identity of the substances. The only thing that has changed for the coffee beans are the shapes. It becomes smaller, but it's still the same coffee beans. So C is the physical change. It's not a chemical reaction. But let's continue analyze D and E. D, baking the cake before and after this process. Cake has become something else. Okay? So baking the cake is actually a chemical change. Similarly, if you have cooking beef, this is also a chemical change. Sometimes this could be confusing for some students. Do remember, before and after you cook the beef, the structure of the protein has changed. So it's different protein, the identity or structure. Okay, so the process is actually called a denaturing process of protein. This process is a chemical change or a chemical reaction. Similarly, when you look at tarnishing of silverware, okay, this is the reaction between silver and oxygen. Rusting of iron. That's also a chemical reaction because iron has become iron oxide. In the tarnishing of silverware, silver has become silver oxide. Okay, so C is the correct answer. Next, let's talk about how to write a chemical reaction. When you write a chemical reaction, the substances on the left side are called the reactants. The substances on the right side are the products. If you want to indicate the physical state of each reactant, we use G representing gas, L as the liquid, S for the solid. AQ represents aqueous solution or water solution. Then, how to balance a chemical reaction? When you have a chemical reaction, as you see down below, CH4 or methane reacting with oxygen, which generates carbon dioxide and water as the products. In this chemical reaction, as you noticed, we have numbers before the formulas. For example, the number 2 and number 2. And number 1 is not written, it's implied. So you have a number 1 here, you have a number 1 here. The numbers before the chemical formulas are so-called chemical coefficients. They indicate the number of molecules that are involved in the chemical reaction. So in this chemical reaction, one molecule of methane reacting with 2 molecules of oxygen gas generates 1 molecule of carbon dioxide and 2 molecules of water as the products. When you balance the chemical reaction, you always want to insert chemical coefficients. You never change the subscripts, okay, not subscripts. If you change the subscripts, you are changing the identity of the substances. That's incorrect way to balance the chemical reaction. This particular chemical reaction is already balanced because if we count the number of atoms before and after, we can see before the reaction, or when you look at the reactants, you have one carbon, okay, inside the CH4, and you have 4 hydrogen atoms because you have one, which is not written, one CH4, all right. You have 4 oxygens in the 2 oxygen gas. Each oxygen gas has 2 oxygen atoms, so it's 4 oxygen atoms total, 2 times 2. Okay. After the reaction, or when you look at the products, right, you have 1 carbon inside 1 CO2. That 1 is not written. Okay, all right, and 4 hydrogen atoms, and the 4 oxygen atoms as well. Because for 1 CO2, you have 2 oxygen atoms. For 2 H2O, you also have 2 oxygen atoms. So you have a total of 4 oxygen atoms. As you can see, for all the elements, carbon, hydrogen, and oxygen, they are all balanced. So the chemical reaction is balanced in this case. Now let's talk about the details how to balance a chemical reaction. If the formulas for the chemical reactions are not provided, or they simply provide you the names for the chemical reaction, please write down the correct formulas for the reactants and the products first. But if you have this already, you can go straight to step 2. How do you balance this reaction? You got to pick one element to start with. So here's how you pick the first element to balance. You actually balance the simplest element. So what is the simplest element? It is defined as the element that appears in the least number of formulas. If you appear on the left side, you must appear on the right side. So the least number of formulas an element can appear is 2. Okay, the next most simple element could be having appeared in 2 formulas or 3 formulas, etc. Okay, so step 2, you balance the simplest element that appears in the least number of formulas. Step 3, you pick the next most simple element from the already balanced formulas in step 2. Then you repeat step 3. Sometimes I call this simple method, because when you look at the method, you always pick the most simple element, which is defined as the element that appears in the least number of formulas. You start balancing that, then balance the next most simple element. Let's look at a few examples. In this chemical reaction, you have aluminum reacting with sulfuric acid. Okay, so how do we balance this? We already have the formulas, so we can go straight to step 2, which is to find out which one is the most simple formula. For beginners, I strongly suggest you write down a table like this. So you have elements, and then we write down the number of formulas it appears in. Okay, right. So when you look at aluminum, it appears over here. That's 1 formula. It also appears here. That's 2 formulas. So aluminum appears in 2 formulas. You look at hydrogen. Hydrogen appears in this formula. It also appears in the last formula. So hydrogen appears in 2 formulas as well. When you look at sulfur, sulfur appears, look at triangle, in this formula. It also appears in the next formula. So sulfur appears in two formulas as well. Now let's look at oxygen. Okay, oxygen appears in sulfuric acid. It also appears in the products. So it's in two formulas. As we can see, all the elements appear in the same least number formulas. So this just tells us we can start balancing any element first. You will be able to balance this equation pretty easily. So let's just pick one way to balance it. For example, if we balance aluminum first, so if we balance aluminum. So look at this whole equation. In this formula, you have one aluminum. On the other side, okay, you have two. So to balance this, we put a 2 before Al. I also strongly suggest you put a 1 before this whole formula, right? Because if you don't put anything over there, you might come back and put a different number over there, which will mess things up. Even if it's a 1 as the chemical coefficient, you put a number over there. Okay? All right. So next, what are we going to balance? So next, we can either balance sulfur or we can balance oxygen. It doesn't matter which one you balance first. For example, let's say we balance sulfur first. So look at this equation, which is already balanced. What do you mean already balanced? That means you already have a number assigned. This number 1 is assigned to this formula. So that's why we say this formula is already balanced. Okay, but we are looking at the sulfur now. We have sulfur over here. Look at this whole formula. Let me erase some of this. So when we look at sulfur in aluminum sulfate, okay, inside the parentheses we have SO4. That gives you 1 sulfur, not 4, because this number 4 only refers to 4 oxygen. Okay, for sulfur it does not have a subscript, or it has a subscript of 1, which is not written. So in SO4 it has 1 sulfur. However, you have a subscript number 3 after the parentheses. That 3 refers to 3 units of everything inside the parentheses. So for this reason, we have 3 sulfur atoms. In sulfuric acid, you only have 1 sulfur. So to balance sulfur, we put the 3 before that. Step 3, now we're going to talk about hydrogen. So we're going to balance hydrogen. So look at the terms that's already balanced over here. For H2SO4, you have 2 hydrogen atoms, but we do have a 3 before the whole thing. So for this reason, you have 3 times 2 hydrogens. That's 6 hydrogens over here. Okay, 6 hydrogens. In H2 on the right side, each H2 gives 2 atoms of hydrogens. So to balance this out, we need to put a 3 before H2. In the end, this reaction is balanced. We can double check and make sure all atoms are balanced. Let's look at another example. In this particular reaction, methane, CH4, reacts with oxygen and produces carbon dioxide and the water as the products. So we have the chemical formulas to begin with. We are going to go straight to step 2, which means we start looking for which one is the most simple element. Then we start balancing that element first, then balance the next most simple element. Let's make a table out of it. So we have different elements over here, and we're going to determine in how many formulas they appear. So the number of formulas. When we look at carbon, carbon appears over here and here. So carbon appears in 2 formulas. If you look at hydrogen, hydrogen appears here and there. So hydrogen also appears in 2 formulas. Now you look at oxygen. Oxygen appears here and here and here. So oxygen appears in 3 formulas. As we can see over here, both carbon and hydrogen are the most simple elements because they appear in the least number of formulas. So we can start balancing this chemical reaction either by carbon or hydrogen. So let's just, for example, let's balance carbon first. Okay, so balance carbon. When we look at carbon, there is 1 carbon in methane and 1 carbon in carbon dioxide. So this is already balanced. But as I previously strongly suggested, I want you to put down a number 1 before the formula, even if it's balanced. So you will not come back and change that to a different number. Step 2, we balance the next most simple element from the already balanced terms, or from the ones that already have a number assigned, like you see in the check mark. So we can either balance hydrogen or oxygen. Which one are we going to balance next? You're not going to balance oxygen because oxygen appears in 3 formulas. So next we're going to balance hydrogen. So when you balance hydrogen here, we have this term is already balanced. Okay, so we start from here. We have 4 hydrogens over here. Okay, on the right side, in H2O, you have 2 hydrogens. So we need to put a 2 before that formula to balance the hydrogen. Right. Now number 3, we only have oxygen left. We're going to balance oxygen. Do remember, this term is not balanced because we don't have a number assigned before O2 yet. When we look at CO2, you have 1 times 2 oxygen. Each CO2 gives you 2 oxygen. You have 1 CO2. So it's a total of 2 oxygen atoms. Inside H2O, each H2O gives you 1 oxygen. However, you have 2 H2O. So for this reason, it's 2 oxygen. This is oxygen, not 0. Okay. So the total is 4 oxygens on the right side. Okay. So on the left side, each O2 provides 2 oxygen atoms. You need to make it 4, so you need to put a 2 before this whole formula. So you have the reaction balanced. Okay. All right. Let's look at another example. This example is more complicated. However, if you follow this method, you will be able to balance it with no problem. So we have formulas to begin with. Now we need to start finding out which element or elements is the most simple element. Do the same procedure. We write down the elements that you see in the reactants and products, and we want to put down the number of formulas it appears in. So first we have copper. A copper, when you see it appears here and there, so that's 2 formulas. You look at nitrogen, nitrogen appears here and nitrogen appears here, so that's 2 formulas. Now you look at oxygen. Oxygen appears here, 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 here. So oxygen is everywhere. It appears in all 4 formulas. Okay. Now you look at sodium, Na, appears here and there. So sodium appears in 2 formulas as well. Next, you look at phosphorus. Phosphorus here, phosphorus here. So phosphorus also appears in two formulas. Okay, as you can see, out of the 5 elements, 4 of them appear in 2 formulas, which means you can start with any of those 4, but not start with oxygen. Okay, so let's balance this reaction. For example, if we balance copper to begin with, okay, in this formula you have 1 copper. On the right side, this copper has 3, so you put 1 here and you put 3 here. Okay, next step, do remember we always balance the next most simple element from the already balanced terms. The already balanced terms means the terms that have already been assigned a number to it. So next we can balance either nitrogen or phosphorus, but we are not going to balance oxygen because oxygen appears in 4 formulas. That's not the next most simple. Okay, so you can balance anyone first, either nitrogen or phosphorus, but not oxygen, not sodium either, because sodium is not appearing in the formulas that have already been assigned a number. Okay, all right, so for this reason, maybe we can balance nitrogen or phosphorus. If you balance phosphorus first, it's a little easier. Okay, but I would like to demonstrate to you if you balance nitrogen first, how you would be doing that, because it involves a little bit of simple calculation. So let's say we balance nitrogen first. Okay, when you look at this formula, I want you to be able to figure out how many nitrogens you have. First layer, you look at NO3 inside the parentheses. NO3, this unit gives you 1 nitrogen. Okay, then you have a subscript outside the parentheses, so you have 2 units of NO3. So this parenthesis, look at that gives you 2 nitrogens, and then you have a 3 before the whole formula, so it's 3 times 2, that gives you 6 nitrogens. Okay, now you look at the right side. Here it gives you 1 nitrogen, so you should have put a 6 over here, right? So next we can balance sodium, let's say, right? Because again, this is balanced, this is balanced, right? Okay, you can balance sodium or phosphorus, doesn't matter. Okay, they will give you the same answer. Okay, so if you balance sodium over here, you see 6 sodium. In this formula, which is not balanced yet, you have 3 sodium, so you need to put the 2. So right now the whole reaction is balanced. If you are concerned about oxygen, you might be wondering, hey, is the oxygen balanced already? You can double check and you will know it is also balanced. Let's quickly summarize how you balance a chemical reaction. If you already have chemical formulas provided, it's very straightforward. You simply find out which element is the most simple element, which appears in the least number of formulas. You start balancing that particular element first. Then you balance the next most simple element from those formulas that have already been assigned a number. Then you repeat this procedure until you finish everything. Next, we are going to talk about electrolytes and the non-electrolytes. Electrolytes are the chemicals that will ionize when dissolved in water. Electrolytes can be classified as strong electrolytes and weak electrolytes. Strong electrolytes, they ionize 100% in water. So strong, that means complete ionization. Weak electrolytes partially ionize when dissolved in water. So the keyword is partial ionization for weak ones. To remember, weak electrolytes are still electrolytes. Non-electrolytes, they do not ionize at all in water. Okay? All right. So let's look at some examples of strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes are, for example, strong acids, strong bases, and the soluble salts. Okay. Strong acids, let's look at these examples. You will have to memorize these 6. Okay. HCl, HBr, HI, HNO3, HSO4, HClO4. Please memorize these 6 compounds. And all other acids, we simply assume they are weak acids, although as a matter of fact they are other strong acids. However, for intro chemistry, remember the 6 acids and all other acids. You simply assume them to be weak. All right. For strong bases, memorize these 8. Okay, 5 of them come from group 1A. If you look at the metal, lithium, sodium, potassium, rubidium, cesium. Okay, 5 of them come from group 1A, and 3 of them come from group 2A. So that's calcium, strontium, and barium. The hydroxides of these metals are strong bases, and the others, then the other bases, you simply assume them to be weak. Okay, all right. Let's look at some examples of weak electrolytes. Weak electrolytes, we have weak acids and weak bases. For weak acids, the most famous one is hydrofluoric acid, HF, and acetic acid, as you see over here. Weak bases, ammonia. Okay, please memorize all these formulas over here, because this will be very helpful when you take your test. Now let's look at what happens when strong electrolytes dissolve in water. As we know, strong electrolytes will completely ionize in water. Okay, so for example, when you have NaCl, table salt, when you dissolve in water, did you notice that we do not see NaCl unit in the solution? When you look at the solution, there is no more NaCl unit. They have totally ionized into the corresponding Na plus and Cl minus. Similarly, for silver nitrate, AgNO3, after you dissolve this in water, there is no more silver nitrate unit. Rather, silver ion and the nitrate ion, silver ion and the nitrate ion, okay, will exist in water because soluble salts have already ionized 100% once you dissolve it in water. For the insoluble salts, for example, silver chloride. Okay, silver chloride does not dissolve in water. Okay. More strict speaking, though, we say a salt is not soluble in water. It simply means the solubility is very small. It doesn't mean it does not dissolve at all. So that's a more accurate understanding of the solubility. I'm going to say it for one more time. If we say a salt is insoluble, it just means the solubility for this salt is small. It doesn't mean it does not dissolve at all. But how do we know if a salt is soluble or not? We have so-called solubility rules that can help you determine that. In the solubility rules, first we're going to determine the generally soluble compounds. Okay, so if if a compound, we are talking about the compound solubility, right? A compound, ionic compound, will always have a cation and anion. Okay, you cannot have a compound that only have the cation. It would not be called a compound, right? So do remember that an ionic compound will always have both a cation and anion. If the cation is in group 1A, okay, you can add some other group 1A, for example, cesium, rubidium, etc. Okay, all right. If it's in group 1A or it's ammonium ion, okay, then no matter what the anion is, this compound will be soluble in water. There is no exception to that. If the anion is nitrate or acetate, then no matter what the cation of that ionic compound is, this salt is soluble in water with no exception. For the compounds containing chloride or bromide or iodide, usually they are soluble, with exceptions if they combine with silver ion. This is mercury 1 ion, lead ion. Okay. So what about sulfate? Most sulfate containing compounds, or we can simply call them sulfates. All right, they are soluble in water, but with exceptions. If sulfate is combining with calcium ion, strontium ion, barium ion, or lead 2 ion, then the compound will be insoluble. All right. Next, let's look at the solubility rules for the generally insoluble salts. Right. So over here, we should change this to generally insoluble salts. Right. Sorry about it. It should be generally insoluble. Right. So if a compound, an ionic compound, contains anion hydroxide or sulfide S2-, then the salt is usually insoluble, with this exceptions. This exception rule is actually the rule we just learned in the previously generally soluble ones. So it's from, if the cation is group 1A or it's ammonium ion, then the compound is soluble. Okay. For sulfide, if sulfide is paired up with calcium, strontium ion, or barium, then the compound is soluble. Remember, most of the time, when a compound contains sulfide, it is generally insoluble. So the exception would be soluble. All right. Similarly, if OH- is paired up with calcium ion, strontium ion, or barium ion, the compound is actually slightly soluble. Right. What about carbonates and phosphates? Okay. When an ionic compound contains carbonates or phosphates, they are usually insoluble. But the exception is the same as what we talked about, is if it's combined with the cation that is group 1A. These are group 1A elements. Okay, if you look at group 1A in your periodic table, you do see these elements. Or you have ammonium ion, then the compound is actually soluble. Okay, let's work on a few practice examples to solidify what we just learned about solubility. So look at which of the following compounds is a strong electrolyte. Strong electrolyte, let's review this. What is strong electrolyte? We have strong acids. Okay, you got to remember those 6 strong acids. Okay, we have strong bases. I hope you do remember those 8 strong bases. Okay, and then we have soluble salts. Right. So the first one, that's a soluble salt. So it is a strong electrolyte. The second one, soluble salt. Okay. How do we know? You look at the solubility, which we will go over a few examples next. Okay. Right. So this one, is a non-electrolyte. This is actually glucose. Okay, right, that's non-electrolyte. Okay, when we look at previous couple of slides, actually we went over that, but we did not specifically mention the examples about non-electrolytes. Non-electrolytes, it does not ionize. For example, water, sugars, table sugar, glucose, right, alcohols, for example, ethanol, methanol, etc. They are non-electrolytes. So the example we just saw, glucose, it does not ionize. Okay, so the correct answer would be D. Which of the following compounds is insoluble in water? So usually you will have to look at the solubility rules, which will be provided when you look at your periodic table. Inside that periodic table provided by the testing center, it includes a solubility rules. Okay, all right. So look at the first one. Basically, we have to break the compound down into ions. So the first one, you break it down, it's the lithium ion and the sulfate ion. You can look at either one in the solubility rules. For example, if you look at the lithium ion, okay, look at the first rule. If it contains lithium ion, it's always soluble because there is no exception. Okay, so this one is soluble. Right? KOH, it contains K plus and OH minus. So if you contain K plus, it is soluble with no exception. So that is also soluble. What about calcium carbonate? So you look at calcium or carbonate. All right. So look at the solubility rules. You just find the carbonate right over there. It's mostly insoluble. Okay. So you look at the calcium. Is calcium included in the exception? No, it's not. Which means calcium carbonate is insoluble. So this one is the correct answer. Okay. All right. We can just finish the next two by analyzing it. Again, we break down the ionic compound into corresponding ions first, so you can apply the solubility rules. Remember, you have to break them down into ions. This break down to sodium ion and the nitrate ion. Okay, when you look at this is ammonium ion. Sorry, not sodium ion. Ammonium ion. When you look at that, ammonium ion, all ammonium ions are soluble in water. Or if you look at nitrate ion, all of them are also soluble in water. You see that? So this is soluble in water. Now NaCl, apparently it contains Na+, that is soluble in water. So C is the correct answer. A substance dissolved in water that cannot conduct an electric current is called, if it does not conduct electric current, we call it non-electrolyte. Remember, non-electrolytes is different from weak electrolyte. And a weak electrolyte is still an electrolyte. A strong electrolyte is also an electrolyte. Okay, these are electrolytes. All right. Okay. Next, we are going to talk about different types of chemical reactions and how to represent them. There's one type of chemical reaction that is called precipitation reaction, in which you see a solid being formed upon mixing up two clear aqueous solutions, as you can see in this example on the right side. Okay, the yellow precipitate or solid is this compound, PbI2, okay, or lead-2 iodide. All right. In the next example, we see over here, when you mix two salts together, there is no reaction. When you mix up Ki, calcium iodide, and the sodium chloride, there is no reaction happening. The reaction does not happen when you look at the beaker. After mixing the two solutions, it stays clear. All right. Next, let's talk about how to write different types of chemical reactions. Right? How to represent the chemical reactions. If we write everything and balance it, as you can see over here, okay, everything is in the same original formulas, and they are in neutral form. If you write them this way, we call that molecular equation. Right? The next type of equation we call that complete ionic equation. In this complete ionic equation, strong electrolytes have been written. Remember, it's only the strong electrolytes. They have been written in the form of component ions. Do remember, you only separate the strong electrolytes, which means strong acids, strong bases, and soluble salts. You only break them into the component ions. Okay? For all other formulas, they stay as is, the same as the neutral form. Okay? So silver nitrate, thus dissolving water, it's soluble salt. How do we know? Use the solubility rules. So it breaks down into silver ion and nitrate ion. Then you have a table salt. You break it down into Na plus and a Cl minus. All right. On the right side, silver chloride. This is insoluble salt. So you stay as is. Soluble salts, you break it down into constituent ions, but insoluble salt stay as is. And the sodium nitrate does dissolve in water, so you break it down into corresponding ions. When you write it in this way, we call this complete ionic equation. And you notice the ions, some ions do not change before and after the reaction. So we call those ions spectator ions. For example, nitrate ions or sodium ions. Right? When you cancel out the spectator ions, you will have so-called net ionic equation. So you cancel out, if you just remove this, cancel this out, you cancel that out because it's the same before and after. Then you will have so-called net ionic equation because the spectator ions are cancelled out before after the reaction. So it leaves the net reaction, which tells you what really goes on in the chemical reaction. All right? Okay. Now let's go over the second type of chemical reaction. We just talked about precipitation reaction and different ways to represent the precipitation reaction. For example, complete ionic equation, okay, net ionic equation, and molecular equation. Now let's talk about acid and base reaction. Acid-base reaction describes the reaction between an acid and a base. For example, when hydrochloric gas reacting with sodium chloride, it generates water and table salt. Remember, when an acid reacts with the base, it always generates water and it generates a salt. Salt means an ionic compound. Okay, so it's always water. Here is a table salt, but again, an ionic compound is also called a salt. So let's look at this reaction. What is the net ionic equation? So let's break this down step by step. Do you remember, we only separate the strong electrolytes into the corresponding ions. all other formulas will stay intact for the net ionic equation. So to write the net ionic equation, we have to first break the formulas down correctly into the component ions. So remember, HCl is a strong electrolyte, so we do break it down into component ions. So it's H plus, so you write AQ, which means it's aqueous solution, and a Cl minus. Okay, and sodium hydroxide is also a strong electrolyte, so you break this down as well. So you write down Na plus aqueous solution, because ions does dissolve in water, okay, and hydroxide. On the right side, water is a non-electrolyte. You do not break it down, so stays as is. L means liquid phase. What about NaCl? NaCl, according to the solubility rules, always keep that periodic table with you, right? So that periodic table does have a solubility rules over there. So you know NaCl is soluble in water, which means it's a strong electrolyte. You will need to break it down into corresponding ions. And this equation is already balanced, okay? If it's not balanced, you have to balance it. This is so-called a complete ionic equation, in which you simply break down the strong electrons, right? Next, to write the net ionic equation, okay, you will have to cancel out the ions that do not change before and after the reaction, or so-called spectator ions. As you can see, chlorine stays the same before after the reaction, okay, and sodium stays the same before and after the reaction. So this means they are so-called spectator ions. You cancel them out. This leaves the net ionic equation, as you can see, which is exactly the same as this one. Okay, that's how you get the net ionic equation. Let's look at a few more examples over here. All right. So this is asking you which of the following is a product for the following reaction. So you have two salts reacting, but no product is given. So how do we know how to write the correct equation? Do remember, for this type of reaction, it's always outside reacting with outside, if it reacts at all. Okay? Then inside is recombining with inside. When you recombine them, you do need to write the correct formula. Okay, so outside and outside, do remember, when you write a formula, it's the metal first. And when you write this guy, it's the Ba2+. When the outside SO4, that's SO4 2-. Okay, you do crossover rules. So Ba will take a 2, sulfur will take a 2, but when you simplify it, you do know a 1:1 ratio will balance out the charge. So that's why it's BaSO4. That's how you get this formula. Okay. And according to solubility rules, check that periodic table, please. Okay. Print out that periodic table, which is the same as the back cover of your lab manual. We have the solubility rules over there. So we do know barium sulfate is insoluble. Then next, you combine inside. So inside means here it's Na plus. Then here is a Cl minus. But do we write it sometimes as, oh yeah, we recombine and maybe you have Na2 and a CO2? That's not correct. You will have to do the crossover in the correct way. So basically we have Na plus. Why do I write Na first? Remember, in the very first classes, we talked about how to write the formulas correctly. You always write the metals first, then the nonmetals. So that's why we write Na plus first. Then you have Cl minus, it's 1-to-1 ratio, because when you have 1-to-1, charge will be balanced. Okay, so it's NaCl. Right, now you balance the reaction. So that's the whole reaction. We write AQ here because it's soluble in water. Right. So what is the product? You have two products over here. Okay. So this is wrong. Remember, it's not Ba2, right? Is this the product? Yes, that is the product. Okay. Is this the product? No. Why? Because it says AQ. If you pick this one, you might think this is correct. But no, it's not correct. The correct one should be insoluble in water. So this is kind of confusing if you don't pay attention to the details. All right. Is this correct? No, because NaCl does dissolve in water, so it should be AQ. We do not have SO2 at all. So B is the correct answer. Let's look at another example. This is an acid-base reaction. So what are the spectator ions? So first we got to be able to write the correct equation. All right. Do remember, it's outside recombine and inside recombine. So acid-base reaction always gives you the inside recombine hydroxide and hydrogen. That gives you water. An acid reacting with a base always generates water and a salt. That's the outside recombining. So you have lithium ion and the nitrate ion. When you recombine it, it gives you lithium nitrate. So you write it down. For this reaction, after you write down the formula, it happens to be balanced already. Okay? All right. So what are the spectator ions? When you try to write the spectator ions, you will have to write the complete ionic equation first, then cancel out the spectator ions. So let's do that. Right. So that's soluble in water because it's AQ, right? You can also look at the solubility rules. So you do break it down into corresponding ions. Okay. And this nitric gas is a strong acid, so it's a strong electrolyte. You have to break it down into corresponding ions. Water on the right side, you do not break it down because it's a non-electrolyte. And then you look at lithium nitrate, it's soluble in water. Check the solubility rules. So you break it down into corresponding ions. Then you notice the ions that do not change before and after the reaction, they are called spectator ions. For example, you look at lithium, before and after it stays the same. Okay. You look at nitrate ion, before and after it stays the same. So they are so-called spectator ions. All right. Now let's talk about next type of reaction, which is called a gas evolution reaction, in which you see gas being generated as one of the products. Usually these reactions are two-step reactions. For example, when you have nitric acid reacting with sodium carbonate, first, when you combine outside, you have carbonic acid, and you combine inside, you have sodium nitrate. However, carbonic acid is not stable, especially if you slightly heat the solution. Okay, so this carbonic acid will break down into water and carbon dioxide. Carbon dioxide is a gas. So if you combine everything together and then write the final products only, you will see this reaction. Okay. We have some other examples. For example, when you have HCl reacting with the potassium sulfide, again, outside and outside, inside and inside, you recombine. That's inside, outside. Do write the formulas in the correct ratio according to the crossover rules, which we learned when we talk about naming of ionic compounds. Okay, so H2S, hydrogen sulfide, is a gas, and it's a toxic gas. It does not smell well either, right? Next example, you form carbon dioxide, and then when you look at the other example, you form sulfur dioxide. If you have ammonium ion, you react with hydroxide, it gives you water and ammonia as well. In an oxidation reduction reaction, or sometimes we simply call it redox reaction. Redox, red means reduction, redox, ox means oxidation. So we sometimes call that redox reactions. Okay. Basically, in this type of reactions, we do see both reduction and oxidation. So what is oxidation? Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay. Here's the mnemonics that will help you remember this. So oil-rich, oxidation is loss. Reduction is gain of electrons. Okay. Please remember the oxidation and reduction should always happen at the same time, because if somebody loses electrons, it must be picked up by another reagent. Right? Now let's go over combustion reactions. In the combustion reaction, a fuel is reacting with oxygen, like methane burning in the air. We talked about this reaction before. All right, let's do a few exercises. Which gas is released from the reaction of calcium carbonate with nitric acid? So calcium carbonate reacting with nitric acid. So do remember, it's outside and and outside. So this outside, outside, this gives you a salt. Please make sure you do crossover rules. Then the Ca2 plus and the nitrate. Apparently, to cancel out the charges, Ca will have 1 and NaO3 will have a 2. That's the crossover rules. 2 goes to here, 1 goes to here. That's how we know. So you write the correct formulas. And you do inside, recombine. So inside it's H plus. We write the H plus first, and then you combine with the carbonate. It should give you 2 hydrogen to balance out the 2 negative charges. So this will be the original product. Do you remember carbonic acid is not stable, so it will break down into corresponding components, water and carbon dioxide. Okay, so carbon dioxide is the gas that is generated in this process. Which of the following sets of reaction will result in redox reaction? The redox reaction, do you remember in the reaction if you see elements, okay, that's one of the key thing you can remember. If you see elements rather than compounds, then if the reaction happens, it will be a redox reaction. That's what can help you. Okay, so that's an element. That's another element. If it reacts, that's redox. Okay. So that is a redox reaction. Basically, for a redox reaction, what you should be looking for is elements are involved in this case. It doesn't mean if there is no element involved, then this reaction is not redox. The opposite is not true. However, if you do have elements being involved in the reaction, it must be a redox reaction. Okay. Let's summarize the classification of different chemical reactions. A chemical reaction can be classified into precipitation reaction, in which you see a solid being formed, or acid-base reaction, you see acid-base neutralization. Sometimes you see gas being generated. That's called a gas evolution reaction. And when you look at oxidation reaction, okay, or oxidation reduction reaction, or redox reaction, inside that you have the loss or gain of electrons. Do remember, combustion reactions are a type of redox reaction. How do you decide easily if a reaction is a redox reaction? If in the reaction you see elements being involved, then that reaction must be a redox reaction. However, the opposite is not true, which means if in the reaction you do not see an element, it does not mean it's not a redox reaction. It still could be a redox reaction. All right. Summarize everything in a different way. All right. Okay. A chemical reaction can also be classified as synthesis or combination, which means you have two or more substance being converted into one. Okay, for example, you have carbon, you're acting with oxygen, this gives you carbon dioxide. That would be a good example, right? Decomposition, which means you have one, you decompose to two or more. For example, you have calcium chloride. When you heat it up, this triangle means heat it up, it gives you calcium chloride and oxygen. If you balance this reaction, to remember it's one compound being converted into two different substances. So that's called decomposition reaction. Single displacement in this type of reaction, okay, an element is replacing another one. So A replaces B. So B was originally here, now it's replaced by A. So that's called a single displacement. In double displacement, you have outside recombine and inside recombine. Do remember, when we write AD, but you don't write this as BC because C was in front to begin with over here. So that's why you want to write the C first. It's CB. All right. Another thing is, do remember these A, B, C, D, they are generic. They don't represent a 1-to-1 ratio. Okay. For example, if you write zinc reacting with HCl, it gives you actually not a ZnCl. You do crossover rules. Zinc carries 2 plus charge. Chloride carries 1 negative charge. So it's CO2 actually. So it should be CO2 plus H2. When you balance the reaction, you have a 2 here. All right, so the ratio is not 1-to-1 ratio, as you can see here. All right. Similarly, if you write a reaction like this double displacement reaction, this is also an acid-base reaction. Okay. So you write this reaction, you've got to have a correct ratio. Okay, then you balance the reaction. Okay. Right. So that's the balanced chemical reaction. Actually, it should be 6 over here. That's the balanced reaction. Let's do a few practice exams before we conclude this chapter. First, what type of reaction is the following? Apparently, it's from 1 to 2 or more. That's so-called a decomposition reaction. Right. Next example, you have 2 combined to give 1. This is so-called a combination reaction or synthesis reaction. Okay. What type of reaction is the following? When you look at that, it's 1 replaced this hydrogen. Originally, you have a hydrogen. Originally, before the Cl, it was hydrogen, right? Do remember the ratio is generic. It's not necessarily 1-to-1, and most of the time it's not 1-to-1. So before that, it used to be hydrogen. Now it's replaced by this thing. Okay, so this is so-called a single displacement reaction, which you can write a generic form like A replacing B, so it gives you AC and the B. As I said, the ratio of the subscripts is not 1. You have to write the correct subscripts. Okay, this is single displacement. Look at the next one. You have 2 compounds mixing together, and as you noticed, the products are the inside and inside combination and outside combination. When you recombine, write the correct subscripts as according to what we have already learned. Use the crossover rules. Recombine the ions, get the correct ratio in the balanced reaction. But as we can see, it's inside and outside, which means it's double displacement reaction. What about redox reaction? Okay. Don't spend too much time on redox reaction, except for that statement you need to know, which is in the redox reaction. Okay, if you in the reaction, if you see any element involved, that reaction must be redox reaction. Okay, let's look at this question. Redox reaction are those in which oxygen reacts with another substance. Yes, that's correct. Okay, or electrons are being transferred from one reactant to another. That's also correct. When you see a metal and the metal react, a non-metal and the metal react, that means you have elements being involved, right? Okay, so it is also a redox reaction. So all of the above are correct. All right, so that's it for today. Have a good day, and see you next time. Bye.